Hello young teens and a very warm welcome to each one of you in today's session. Are you all geared up to understand what new I have presented for you today? Well, let me take you to the very fact that we just now completed our very journey in the city of sets in the mathematical world. And now we began our very tour to the very next city, wherein we had started our quest of understanding how to construct another new set with the help of just available 2. And in order to understand that, I had already told you the very name of such new set, which was the Cartesian product of the two sets which you had taken previously. But did I directly jump on to the very concept of Cartesian product? Well, if I had done so, nothing would have entered your brains. And therefore, firstly, we began our study with the very concept of ordered pairs. Do you all remember that these were pairs of two objects which were not just any ordinary pair, whereas they were something extraordinary? I told you that if you pick up two distinct objects, suppose object A and object B, and I write two statements simultaneously that I have a pair of object A and object B, and on the other side I had written I have a pair of object B and object A. Well, in English, they both mean the same things. But what if I induce a certain kind of order inside them? What if I focus on which element I am speaking first and which element I am speaking the second? That is what the very essence was which made an ordinary pair into an ordered pair, wherein it was superbly important to basically stress on the fact that which element would be sitting at the first position and which element would be sitting at the very second position. And therefore, we understood that with the help of two distinct objects, I can make two distinct ordered pairs, wherein if I have an object A and object B, one pair I can make is first I am going to place object A and then I am going to place object B as the second object. On the other hand, I can put object B at the first place and A at the very second place. These are the only two ways in which you can make two distinct ordered pairs with the help of available two objects. Because we understood the very next concept that equality of two ordered pairs does not depend only on what objects have been used to make those pairs. In fact, the very ordering should also be the same. And this brought us to the very next concept of equality of two ordered pairs. By the very concept of equality, we also learnt that just when we know that when are two ordered pairs equal, not just by the two objects being the same which are used for the construction of those pairs, in fact, if in the first pair, one object is sitting at the first place, the second pair should also at the first place have the same object. Similarly for the second object also, once we understood the very fact and the definition of equality of two arbitrary ordered pairs, we had also dealt with a question wherein by the very concept of equality, we had solved the unknowns which were available to us, small a and the value of small b. Do you remember that? I'm sure you would. After that, once this concept was over, this brought us to the very idea that we need two objects in order to define a pair. And it would be the next task then to order the pairs and then declare them as ordered pairs. But how to bring two objects into picture? Well, that was a serious question, but we had an answer for that. which was that if I bring before you two sets, distinct two sets, and I allow you to pull one element from the first set and pull another element from the second set, well, in that case, you will have two objects in your very hand, and then you have two distinct possibilities to order them and make ordered pair out of them, which is actually denoted like this, where A is sitting as the first object and B is sitting as the very second object. But there was a question. Once you have two objects from the two sets, how to order them? Well, there are two orders available. Which one to choose? For that, it was superbly easy and advised to order the sets which you have taken. Once you order the sets as set 1 and as set 2, well, that automatically labels the elements inside set 1 as the first elements, and it labels the elements inside set 2 as the second elements. All the ordered pairs thus formed will have first element coming from the first set only, and will have second element coming from the second set. Therefore, ordering the sets is enough to understand the order of the pairs. This concept basically allowed us to form all possible pairs wherein the first object comes from the first and the second object comes from the second set. This collection of all pairs, basically we just collected them all together, made a set out of it and declared it as the very Cartesian product of the first set and the second set. And this was denoted by what? Well, this had a very nice notation. You just have to write the first set, multiply it with the very second set. This particular notation was used in order to write the Cartesian product of the first and the second set. Well, I also told you, what if I swap the orders? I make my second set come at the first position and first set go at the second position. We also discussed a case wherein instead of second, I put first again and get the Cartesian product of the first set with itself, and then replace 1 with 2 and get the Cartesian product of the second set with itself. These were the 4 very interesting cases based upon the Cartesian product which we discussed, and this was the very new set apart from what all we have learnt in set theory, which was formed with the help of two available sets, the very Cartesian product of the two sets. If you remember, the very last article which we did in set theory was not just finding out the new sets with the two available sets, like the union, the intersection, the difference, the symmetric difference and the complement. No, the story did not stop here, because after that we started our quest of understanding how many members are actually sitting inside the set. The idea which is the next is, if you know the number of members sitting inside set A and sitting inside set B, can you find out in any way the number of members sitting inside the newly created sets with the help of A and B? Well, let me remind you something. If you have already set A and set B in picture, with the help of these two sets, the very first set you created was A union B. Suppose you know how many members are sitting inside set A and you also know the number of members sitting inside set B. After that, we can find out very easily number of members sitting inside set A union B, which actually is number of members in the set A plus number of members inside the set B minus number of members in the set A intersection B. Remove the common elements from this sum, and that is when you get number of members in A union B. After that, the very next new set which we created with the help of available 2 was the very difference. From all sitting inside set A, just chuck out the members sitting inside set A which belong to set B. And that is when you get the set A minus B from A and B. Can you find out the number of members sitting inside the set A minus B? Of course you can. That number actually is number of members inside set A. From that you just remove the number of members in the set A intersection B, and that's bingo. You have got the number of members sitting inside the difference of A and B. A very similar formula is for B minus A also. After that, the third new category of set which we created was a very handsome name given to the new set, the symmetric difference of two sets, which was denoted by A del B. How many members were sitting inside A del B? Provided you know how many members are sitting inside A and B. Of course you know this number also. Well, I don't need to do anything. I am just going to take the number of members in set A, added the number of members inside the set B, and subtract 2 times the number of members in the set A intersection B. This was the very formula used to find out how many elements are sitting inside the symmetric difference. And the fourth category of the new set which we created with the help of available just 2 was A complement union B complement. This new set we created, and we were again able to find out how many members are there inside this. And this basically by De Morgan's law turned out to be A intersection B whole complement, which actually made sense to write number of members in the universal set minus number of members in A intersection B. Just chuck out the members of A intersection B from the entire universal set and you are going to get its complement, or A complement union B complement. Once we had accomplished the task of creating new sets and then finding out the number of members in these new sets with the help of just knowing the number of members in A and B, the next new set, the very fresh, the very new entry to this world is the Cartesian product of two sets. Suppose I give you this new set formed with the help of A and B, which is my very fifth new set. I have A cross B, which is the Cartesian product of the set A first and then set B at the second place. If you know the number of members sitting inside set A and set B, are you in any way under a position to find out the number of members in its Cartesian product? What do you think should it be? Well, that's a quest which we have to solve today. Let me unfold to you the very formula, the very answer to this interesting query, and then this list will complete. Let's start with a very interesting example. Suppose I take my set A to be equal to 2, 4 and 6, and I take my set B to be equal to just two natural numbers, 1 and 2. Now, I am interested in the set A cross B because that is what's cardinality I want to find. Therefore, I am basically interested in something known as A cross B. The moment I have written A cross B, it is enough to declare that my set A is the very first set and my set B is the very second set. Now, first of all, in order to find out the number of members in A cross B, you should be aware about the number of members in the set A and the number of members in the set B. Do you know that in the example? Let's check out. A is having 1, 2, 3 members, okay? My cardinality of A is 3. This is how we wrote it. Cardinal number associated to the finite set A is 3. After that, going on to set B, how many members do you think are sitting inside set B? Of course, it has just 2 members, and therefore cardinality of B, which is the number of members sitting inside set B, happens to be 2. And therefore, I am very much aware about how many members sit inside my set A and how many members sit inside my set B. So what do you think? Is this information enough to find out the number of members sitting in A cross B? Let's try and unfold that. Because my A is the first set and B is the second set, I am going to draw A first and I am going to draw B the second. This is my set A and this is my set B. I am interested in its Cartesian product, wherein I know my A is the first set and B is the very second set. The moment you order the sets, you already have the elements ordered. There is no hustle, no fussle about the ordering of the pairs. No question about that. Because A has members 2, 4 and 6, B has members 1 and 2, and you already know that 2 is my very first element, 4 is also 1 and 6 is also the first, because they are members of the set which is first. And 1 is going to be my second, this is going to be my second, because they are sitting in the set whose position is second. And therefore, just by the position of the sets, we are successfully able to position our elements. Now, the only turn is to form the pairs, because you already have the ordering. In all the pairs that we would be forming, the first position will be occupied by only these 3 elements, because only they have the permission to sit at the first position in all the pairs, and they have the permission to only sit at the second position. Therefore, all the pairs which we would be forming will have only these 2 numbers sitting at the second position and these 3 at the first. Do you remember how we used to form the pairs? Let's start that procedure. Just separately write down the elements of the set A which are first and elements of set B which are second. Now, keep account and keep your focus right here as to what I am going to do next. Fix one element of set A. I have fixed 2. Pair it up with every element of set B. The moment you pair 2 with the first element of set B, you get the ordered pair 2, 1. The moment you pair 2 with the second element of B, you get 2, 2. This means one element of set A is giving me 2 ordered pairs. Corresponding to one element of set A, I am getting 2 distinct ordered pairs. How many pairs am I getting? 2. What is 2? Basically, how many members there are sitting inside set B, those many pairs I am getting corresponding to my element 2. Therefore, this 2 is fixed at the very first place. How many members or how many pairs am I getting with the help of this 2? Those many pairs, as many there are members inside the set B. So basically, 2 is giving me 2, which is same as cardinality of B pairs. Okay? This particular 2 is giving me 2 pairs. But what is 2? 2 is cardinality of B, and therefore I am getting cardinality of B number of pairs with the help of one element of set A. Let's move on to the next element of set A. This 4 also goes and gets paired up with 1, and then it goes and gets paired up with 2. So this 4 getting paired up with 1 and 2 gives me 4, 1 and 4, 2 as the ordered pairs. So again, what is happening? the second element of set A is giving me those many ordered pairs as many there are members inside set B. That means the second member of set A also is going to give me 2, which is same